Okay, let's talk about how to do the data analysis or data processing for your consolidation lab. First of all, if you go to the data sharing spreadsheet online, you should be able to find this spreadsheet. And the consolidation tab, you find all the data, and the data pretty much like make up with three parts. First is the data, the specimen preparations. So each tells you what type of soil is it, the physical measurements like the diameter, the height. The the soil is confined by the steel rings, so all the mass and what type of loading frame ratio is it, all the informations. And then like you also have the water content calculations that you need to do, and just like a water content test, so the number have done for you already, like the range of the can and the range of the wet and dry soil. So with that, you should able to calculate the water content. And we do the water content test before we start the consolidation test. So we will trim the soil samples, feeding into the wings. So the soils that get trimmed off, and then we'll do water content tests. And after we finish the whole test, again, the whole test will last could be 2 weeks to finish all the loading. We talk about the loading steps here. So during the consolidation test, each loading step will cost 1 day. So actually, it's about 2 weeks to get the whole thing done. And after 2 weeks later, we finish the consolidation test. We remove the soil samples from the rings, and then we will get a little piece of the soils, and then we do a water content test again. So we measure the water, the wet weight and the dry weight. The dry weight come from the ovens. Then with those informations, then we can calculate the water content after the consolidation test. So hopefully those two numbers are comparable. If they are off too much, you could be indications that something wrong with the test. If just a little bit change of the moisture, then which tell us is a confirmation test that it is a valid test. And with that, with knowing the water content, we can also calculate the initial void ratios. Remember the equations that we have. The George Washington's is a soil engineer. So which means the void ratio here, the E, can be calculated by using G sub S times the water content. So the G sub S is given to you on the spreadsheet. So you know the G sub S and the water content that you have just calculated. You may want to use the average between the two measurements. You know the water content, you know the G sub S. We assume the saturations is 100%, so S equal 1 in this case. Then you can calculate the E naught. So that is the first step that you want to do. You calculate those water content and also the initial void ratios. And I let you to do the work here rather than doing everything for you. The next is the machine deflections data that we also collected. So if you watch the lecture studios, Mr. Cam has walked you through how to perform machine deflections. So here's the data, the raw data that you get. But what we need to do is correct those data before we do anything. Well, first thing, for this spreadsheet, is the online spreadsheet. You are not supposed to do any calculations or make any change on it. So before you mark any a change on it, I did a bad example when I do the sample preparations. But actually, the first thing we should do is to download the spreadsheet on your own computer. In this case, my own computers, to work on it before making any changes. So now this is on my computers, and I can do the changes that I want. Next, for the machine deflections data, I need to do the corrections before I able to use it, because the data here is is raw data, and this is not ready for engineering use. And this is a direct measurements from the corresponding stress. So what it does is, like, for machine diffractions, the purpose of it is to find out to quantify the soft part of the machines. Because when we loading on our soil specimens, when we put the loading on the loading frame, it is actually it is loading not just only the soil but the whole setup. And eventually we will be putting a lot of a lot of a dead weight on the machines. So 64,000 PSF right there, that would corresponding to almost 200 pounds of loading. If you have that times the area, then you can find out the loadings in pounds. And that's a lot of and then also we have a loading frame, loading arms of almost 10 times. So we are talking about almost 2,000 pounds of force putting on our machines. So our machines is made up with metals, and under such a high loading, even metal can deform. And our whole systems, will also include the stones, the porous stones, the filter papers, and all those parts come together, sandwiched in the soil samples, and also other metallic parts throughout the machines. So under such a high loading, it can deform. So we want to separate those machine defections from our soil defections. So the way we do it, just like the lecture studio that Mr. Cam demonstrate, we will do this with a dummy steel disc to replace our soil. So the same like a loading procedure. So we will be loading the steel disc with all the other part of the machines, the same loading schedule. Now we quantify how much is deformed. So we assume that the steel disc that we paste the soil samples, you'll be rigid enough that you're much relatively rigid than the other part of the machines, like the porous stones and also other soft part of the machines. So whatever we measure here will be just the machine deflections which reflect here. So the way it works is first, we read the dial gauge. So this is the dial gauge reading from the very beginning, and then we put on a loading that weight equivalent to 125 PSF on the machines plus the steel disc, and this tiny bit of deformation. So we expect very small change because under such a small loading. So that will be our machine defections for this particular loading. And then we ramp up the loading to the highest level, and then that would be the loading that we got. So that what we do. And to correct this a raw data, first we need to zero our data, because when we start our loading, the dial gauge that we work on, it won't start at 0, and you don't want to start with 0. You want to offset a little bit, make sure the dial gauge is at a good working range. So what we do is we have readings minus the initial readings, and you want to anchor it. So everything minus the reference 0 right there. And then you realize that it's kind of interesting because now everything becomes negative. And it is because we have a polarity issue need to take care of. And why we have such a polarity issue is because the way that the dial gauge read, or the polarity of the dial gauge, is opposite to our geotechnical conventions. Geotechnical convention is compressions is positive, which means going down is positive. So for example, if we have a dial gauge here, so for example, if this is our dial gauge, so point for a dial gauge, pointing down is negative, and then going up is positive. So that's how the dial gauge think. But in our geotechnical world, so this is our soil samples, for examples, and in fact, going down is positive, and going up is negative. So in order to change that polarity, so because again geotech, right, the formations compressions is positive, but tension is negative. So we talk about this in 366, and now we need to take care of this polarity by multiplying this one by -1. So we'll change our polarity because of that. Then now, this set of machine deflections data will be ready to use. So that should be your week number 1 exercise. When we were in the real lab, then that will be the machine deflections correction, the machine deflections exercise. And then throughout the 2 weeks, actually, we will be let the soil specimens to start our real loading. And after the machine deflections, what happens is you take out the steel disc. We will trim our soil samples. So now within the steel wings, it is the soil samples, and then now we can start our loading schedule. And our first day, so this will be day number 1. The data that we collect under the stress of 125. So we put a small loading on our soil specimens, and at 6 seconds. And so first of all, we read the dial gauge before we start the test. So those are kind of like a 2 separate tests. So so the dial gauge could be a little bit different. But now, you have your dial gauge initial readings, and then you read the initial readings, and then you add the small stress on that, 125 psf for this case, and then at 6 seconds we make our first reading, at 15 seconds we make our second reading, so forth and so on. And we will come back to the lab the next day. So this is 24-hour readings, and then we will make our next final readings. And then after that, we will put on the next level of loading, still small loading, just 250 psf now. And then we will, this is day 2, and then we will continue our recording of data according to the same schedule. So if we start this about maybe 3 p.m. of the day, and then this reading will be 8 hours from that, so that could be 11 p.m. of the date. And then the next day again, we will come back and then make the reading again, so on and so forth, and then so this day number 3, and so forth and so forth, until to the point that, so this schedule here is same as this schedule there. So this is 125, we get this readings, and the 250 we get this readings, 500 we get this reading, so forth and so forth. And you can see at some point of throughout the 2 weeks, we will do our unloading. So we kind of make a loops right there, loading and then unloading. Okay, so those are the raw data that we get, and again, those are not ready for us to do our engineering use. We need to correct it. So the same procedure. First of all, we need to zero our data. So we will use this to subtract the very beginning of the data that we have when we start the test. So we zero all the data. And then the next, yes, we will do the same thing again. So we'll zero the data for the next loading, And again, we will subtract from the very initial readings, right? You need to before we start the very first step of loading. So we zero the data for all of them. So you need to do each of it until to the end. And then like we also need to take care of the polarity by having this 2 times -1. Oh, and then now, wow, if you say why this becomes negative, and we know that like we don't expect negative to be happen when we do our machine deflection tests, but at the very first steps of our soil response, so I would call this a machine response, but this part is a soil response. And when soils is subjected to very small loading compared to what it has been experienced, so what we do is like we treat our soil samples from the ground and then bring it to the lab. So from the deep ground, we bring it to the lab. Sitting on the table at that point, we release all the stress. And now you are putting on a very small loading, 125 psf, compared to like what it used to be at the ground. I don't know what is it, depends on the project, but you will be a number much higher than that. Then you are in a process that kind of like let the soils unloading itself, because in the ground it used to be like a high loading. Now you just have such a small loading, so which means like when you assuming you do everything right after you zero the data and also take care of the polarity, the mismatch between the dial gauge and the geodetic conventions, yet you still get a negative number, means you are expecting the soils to be swelling. And which this cases makes sense because you have such a small load. So if these are soil samples, if you go up, it's negative. Go down is positive. And in the case when you go up, it could happen is because the soil is swelling rather than the soil is consolidating or deforming when you go down. So you may expect a negative number at the beginning just because you know that swelling could happen. So that is the very beginning part. And you will expect like at some point like throughout the test, all the swelling is done. Then like you will see that in fact the deformations start to become positive instead of negative. So what we're doing here is taking care of the dial gauge readings to correct it. Okay, so after what we have correct for the polarity, the next thing is we correct for the machine deflections. So for each loadings, we have already find out or correct for the machine deflections data. So again, like what we are capturing here on this part of data is we correct for the zero. With zero data, we correct for polarity. At this point, it is the soil response plus the machine deflections. So that's why we need to single out the soil deformation by subtracting this set of data by the machine deflections that we have already been quantified at each stress level previously. So to do that, we subtract at 125 PSF stress level. We subtract all of our data with the machine deflections that we find out at this stress level. And since we're looking at the soil plus machine deformations data for 125 PSF only, so we subtract everything with the same number, because like when we do the machine deflections, it is like by each stress level. So now we subtract everything with this number, and then we pull it down. So now we correct for the machine deflections, and what we find out is the soil deformations only. So previously is the machine deflections plus the soil deformations. Subtracting all of them, single out the soil deformations by subtracting the machine deflections measurements that we make for 125 for this particular stress level only. Then what we make is the soil deformations data. We got it here. So we need to do this for all the different stress level. Then also we do it, repeat the same process for the 250 for examples. Here we subtract all the soil plus machine deflections deformations with the machine deflections at 2050 PSF stress level, and we need to subtract everything with the same number at the stress level. So that's why we anchor it. So at the end of the day, we got this corrected data. So this set of data will serve as the final set of data that for us to plot out the time settlement curve. Mr. Cam on another video, he explained in details how to come up with the C sub V parameters. If you plot this out, this is the time that you get from here, and also if you get this the wheel soil deformations, so after all the corrections, then you need to do both log time method and also the square root time method, and then you for each stress level you will get different C sub V values. So you may get a curve like this at the beginning for the data, the part of data that is swelling. Later on you will see a curve like this after, like later on the later part of the test. When you come to high stress level, then you expect compressions rather than like soil swelling. And also you do it for this square root time method. Then each stress level you will get two different C sub V values, and you need to do all of them. So you have 14 different stress level. In total, you will have 28 different curve, and come up with 28 different C sub V values for each lab report. And this could be the most tedious lab report that you have, but you have 4 people per group. So divide the work fairly among your group. So after that, then the next thing you need to do is to work on is that get the E log P curve. The E log P curve will give you. So we talk about this in CE3680, the E log P curve. At this curve here, for examples, we talk about this, how to do the Casagrande deformations. So we talk about all this in CE3680. So those are the E log P curve. And to generate those curves is very well. At the end results, those curves is very good because very useful for our design, because it gives you all the parameters we need, the maximum path pressure using the Casagrande method, and also the so this is the Casagrande method. And also have the C sub R and C sub the recompression index and C sub C compression index. And Mr. Cam has another lecture studios to talk about how to get all this after you generate the data. But now it talks about how to calculate those E log P curve. So first, for each stress level, you need to gather the 24 hours or the ultimate ultimate deformations for each particular stress level. I like ultimate better because we use 24 hours for this test, but in the future you have different soil types, the durations of each loading may change. But anyways, for each each corresponding stress level that we talk about, so those are the corresponding stress level, and the ultimate deformations will be the end readings, that end corrected reading that you got. So this will be that one, and then the 250 will be this one, and so forth and so on. And you need to do all of them. You need to calculate all of them. So after you get like this, like I call this the delta H, the deformations for each corresponding loadings, then you need to convert this delta H to delta E. So you want to, because this is a E log P curve. So you want to, at the end of the day, you want to represent the whole thing as a void ratios. But before get to the void ratios, you need to get the change of the void ratios. And the change of void ratios is related to the change of the deformations. And it can be proved through a phase diagram. And we talked about this already in CE3680 here. So on this particular slide, through the phase diagram, we prove the relationship between the delta H and delta E. So if I highly recommend you to go back this lecture, particularly on this slide. It helps you walk you through how the derivations was done in CE3680. And at the end of the day, through the whole process, we proved that the change of deformations is what we measured. You can relate to the change of the void ratios by this constant here. Pretty much it's just the initial void ratios and the initial soil height. Those are the physical parameters that we can measure for our soil specimens at the beginning. So this is the information we have already, and this is what we measure. So with this, we can calculate the delta E, the change of the void ratios. So for our test, the original height of the specimens is given you here. So the H naught is 0.75. So this is the H naught. So this is the H naught we got, and this is the E naught that you calculate too. Oops. And the E naught is equals to these equations, the George Washington soil engineers. So here I just assume it as 1 because I don't want to do everything for you. You need to calculate yourself how to calculate E naught. And the E naught, it can be calculated from these equations. Pretty much is the G sub S times the water content, the initial water content. I didn't calculate water content for you, so you need to do it yourself. So you know the water content, you know the G sub S, and you know the saturations. Because we soak our soil samples for such a long time, so we can assume a fully saturated, full saturations. So S equal 1, and then you know G sub S, you know W, then you can find out the initial void ratios. I put in 1 here, but it's not 1. I want you to do it, so you need to go back to calculate the initial void ratios. So the delta E will be equals to E naught plus 1 divided by H naught, and then times the delta H, which is your measured values. So you calculate here, you find your delta E, and then so on and so forth. You can find all the delta E, which is the change of the void ratios for the particular stress level. And the void ratios will be equals to the initial void ratios minus the change, and the change is the delta E, and that is the void ratio that you have. So you calculate all of them, and then after that, this is your E, and then you know your stress level right there. You can plot out this curve. Oops. So this is the void ratios. This is the whole column that you calculate here, and you do your log P, which is log vertical stress, which is here. You in the log scale, and then you know how you plot out with the versus the void ratios. Then you should get a curve like this. You have a little bit swelling going on, so the curve maybe look like that, the initial part, but that's okay. And at the end of the day, those two slopes will parallel with each other. You can calculate all the C sub C, C sub R, and also the approximate using the Casagrande method. You can find out the P sub P, or the maximum pass pressure. So Mr. Cam also has another like a clip to walk you through how to calculate this. So make sure you try. And at the end of the day, like I didn't like do the whole thing for you, but I pretty much walked through you most of it, and I hope this helped. And if you have any questions, please feel free to contact me or Mr. Cam. And again, like that's quite a bit of work, but if you can do this by yourself, hopefully like you understand this. You even don't need to look at my tutorial or go back to look at this. You can like do everything yourself on a blank spare sheet. If you can do that, I call you understand the whole thing. I highly recommend you